Recording. Triple integrals. It's triple the fun, but quadruple the pain. Right. Do you know Dr. Payam YouTube channel? Does anyone know it? Oh, you see, some people do, right? So that's his jokes. I copy paste from his lectures. So Dr. Payam is one of my best friends. He's visiting me the next week. If you want, I can bring him in because he definitely has his plate from YouTube channel and everything. He's very famous. People do stop us, even in Arizona, and ask to take picture with him. So I'm the one who is doing this like touristic thing, taking picture of him because he became that famous. Dr. Payam channel is amazing for upper level math classes. I don't have those videos because I did not teach them yet. He has amazing linear algebra class, discrete math, proofs, theorems. He's very good in explaining. It's in my YouTube channel, his link, and in general, you just can write down. Dr. Payam channel is amazing. Many people survived upper level math classes through his channel. So that's, Professor Leonard is people's favorite. His videos for upper level classes are amazing. Triple integrals for now will be the same as double integrals, so don't get scared. The process is the same, but the applications are different. So let's do example right away. Calculate the following integral, where E is a tetrahedron in the first octant bounded by 6x plus 3y plus z equals 12. And the integral now is triple integral over E, and inside there's a 6z, for no reason. So this is the interesting idea, bless you. For now, we're ignoring this thing inside, just like before in double integral. That is some kind of, object floating somewhere. What we're talking about right now is this E is supposed to be below all the integrals. It's just hard to type it when you want to type nicely. So this E is now 3D, three-dimensional object. Before, on the exam 2, we were asking you, can you reverse the order of integration? What did you do? You draw something in 2D. You draw a triangle with a parabola or a square root of x. 2D picture. Now this will be 3D picture. So the whole thing is 4-dimensional. So that's how we're going to upper dimension. Well, tetrahedron is indeed a 3D object. Here it is. Step 1. Sketch the picture. That's exactly what we do for E. Before, E was 2-dimensional. That's whatever is below the integral sign. But the moment we added one more integral, we increase the dimension. So now that thing below, which is your domain, is itself a 3-dimensional object. Isn't it cool that 3-dimensional object is the domain? So the output will be 4-dimensional. How cool is that? This is how tetrahedron looks like. Draw it. Has 4 vertices, 4 faces, 6 edges. And you also can find now intercepts. So we want to actually build the integral knowing all the edges, right? So I don't know the edges. Like, what are those things? This is the one that will help me to build whatever is below and above of each integral. What I do know that it is in the first octant bounded by 6x plus 3y plus z equals 12. What does it remind you, this equation? What is that? It's a plane. So we're going to use that to find points of intersections. Find intercepts. Intercepts. So it used to be points of intersection. Now it's in second, higher dimension. It will be maybe planes of intersections, lines of intersections. So Z first, let's do bullet point. Z intersection is, do you remember? So let me write down the equation. 6x plus 3y plus z equals to 12. So we're using this. Now, first bullet point, z intercept. how to find any kind of intercept, x-intercept, y-intercept, z-intercept. Do you remember the rule of thumb? General idea is what?
Intercept like z set x and y to 0.
X and y 0. Everything else is 0. Exactly, thank you. When you intercept somewhere, that means only that stays a variable. Everything else shrinks to nothing. So we set all other variables to be 0, plug them in, and you have 0, 6 times 0 plus 3 times 0 plus z equals to 12. Okay, so z equals to 12. Put this in the box. That is my solution for now. That means that, well, we're gonna use it later. Now let's find all others. You can speed up if you want. It will be y-intercept. Plug x and z to be 0. Y become equals to 4. And finally, x-interception. That will be x equals to 2. Here they are. So from the tetrahedron, we need to cut off using those planes. They're cutting off stuff. And this is what's left. It's only in the first quadrant, that it says that, in the first quadrant. And now we know the points. So y, here it is, equals to 4, x equals to 2, and z equals to 12. Those are the planes we have. So you know what is height? Well, while you're drawing it, I will just wait a little bit. Z is not fixed. Z will be a formula. What kind of formula? This formula, z equals 12 minus 6, x minus 3y. Can you guess where we get this formula from? We took the original one and solved for z. The original one was this one. Solved from z. So that's the height, you see? The height of this 3D object is not fixed. It keeps changing with respect to this plane, which is tilted. The tilted plane is 12 minus 6x minus 3y. Now we're going to start building the triple integral carefully. So I'll write down the triple integral. My way is to start writing them down while I'm thinking. Some people write down all inequalities first, and then they write out the integrals. Do whatever you like. So do whatever is easier for you. I like to do it in the process of my thought. So I'll write down one integral, have some space between them, because some of them will be equations, or basically functions. Then I will skip the space. Well, actually, I don't have to skip the space. 6z was given, and I have dx. Oh. We can choose, I guess. We can choose the order. Let's do the way I have it in my notes, and then I'll explain you later why. dz, oh, actually the order is given here. dx, dy, dz. Why do I have dz, dy, dx? Let's follow my notes, and then I will remember why I had it. dz. So let's do z first. Oh, probably because it's more obvious. Z goes first. Z is between those two functions. The floor, how did the floor came from? Because it's the first octant, so we don't go to the negative z, so we stick to the xy plane. So z is the height of this three-dimensional object here, and the height is changing from equation to equation, which is from z equals to 0 till z equals 12 minus 6x minus 3y. Maybe I should color code it like this. Z is in blue. And this is how we're building it. This is step 2. Step 2 will be in red. It's kind of the most important. Inequalities. Inequalities for everything. So we only have 3D is going on only for Z. And after this, we're going to decrease the dimension. Z is the only one that's happening in 3D. And the general idea is Z is from small stuff object till big or large object. And in our case, it was from the floor, Z equals to 0, till the plane 12 minus 6x minus 3y, like so. And remember, those are functions, z equals in blue. Maybe put a note here. Why do we have this corner of the room? Because we were told to use first octant. First octant. It's like first quadrant, but in 3D. Okay, so we finished Z. Z was a three-dimensional thing. So we can now go into two-dimensional. The moment you finished with, let me move this away. Put here. The moment we finished with this inside part of the integral, we're done with a 3D object. And now we're going to double integral. And we know that in double integral, we know how to work with it because we already learned it. Let's do dy dx. So step 3, now we do inequalities in blue, inequalities in 2D. That will be dy and dx. So use or decrease the dimension. Use 2D, which is two-dimensional, right? Two-dimension for x comma y, like so. That means I need to draw only x and y axis in the picture of what is happening on x and y. That is where, if you're good with visualizing things, that will help you a lot. Are you good with visualizing things? That's, I would say, is the hard part. Do you see what is happening with x and y? I can help you with understanding that this is a floor of my picture. So I'm zooming in the floor. This is what is happening. The problem is the way we draw 3D is a bit confusing when we want to go to 2D. Positive x is pointing towards me, positive y is pointing to the right. I want to flip it the way we got used to it. X positive should be to the right, y should be up. So maybe the idea is you take this positive y and the whole object, which is a triangle, and move it up, right? Then y will be at the top, x will be to the right. So you take this triangle and move it up. This is one way of seeing it. If you're good at that, good job. Sometimes I feel when I'm stressed, that 3D visualization stucks and I cannot do it, during the exam and stuff like that. So what I do is I actually put points. Points are a very reliable thing to do. I know that on y-axis, it should be from 0 to 4. I'm going to put that here. From 0 to 4. I know that on the x-axis, there should be from 0 to 2. Okay. From 0 to 2. And I know that 4 connects to, see, diagonally. So I'm going to put it here. Yay, that's a triangle. Does it make sense? So either you just revolve it the way you see, revolution helps here, or you just draw it and then you don't mess up. So rise versus run instead of 3D thing now. And now we're going to do that thing we learned for the exam too, because now we basically working with double integral again versus triple integral. So we need to figure out what to do with the last two integrals. I decided to do dy in blue. dy. Y is running from a function to a function. Remember, the outside integral should be number. Insides are functions. Not always, but usually they are. So it should be y equals and y equals. Well, we know already. Hopefully you figure out how to do it before the exam. Or watch my video where I'm explaining it several times. Y is running from a function at the floor to the top, right? Y is height. Y is rise. Rise versus x is run. So it's rising from what function? Y equals what? 0, and end up hitting what function? Y equals? What? 12 minus 3x. 6x. 4 minus 2x. How did you get any of this? So let's see. Let's write down the guess. 4 minus 2x. What? How did you get that? Way number 1. You just create the equation of the line through 2 points. We know that. The formula for that, y minus y sub 0 equals m x minus x sub 0. And there are other formulas and stuff. Yeah, but we're not going to do that. What is the other way? We know this formula. We know actually this line. This line is coming from this tilted plane, which you see right in front of you when you look at this tetrahedron, right? It's a plane. It's a bird. It's a Superman. In this case, it's a plane, and it's cutting through the floor. So the line we are working on, the green line, is just a cut of this plane when there is no 3 dimensions. So z is 0, right? We literally actually said it here. Floor means z is 0. So I will take this equation we had, z equals 12 minus 6x minus 3y, and find the intersection with the floor. So plane, that's a tilted plane. Maybe write down tilted plane. And the floor. But professionals will watch this video and they will say that I'm not smart enough. But actually, that is also a plane. But what I mean is, it's a floor. So in 2D, we're going to find this intersection. So we're going down to the 2D. Getting rid of z. We're going to have 12 minus 6x minus 3y equals to 0. And I skip the simplification, divide by 3, blah, blah, blah. And you end up to be 2x plus y equals to 4. That's what's happening. This is the line. So from here I can solve for y. And now I know what is going to be on the top of the second integral, the one in the middle, the dy. Let me zoom in and wait a little bit. So let's see, that was given. And then the floor, because of the first octant told us that the floor will cut off everything. We're finding intersection in 2D. Does it make sense for now? Is it weird? Also in 2D, we're gonna call this D. So we're jumping from the 3-dimensional E below all the 3 integrals. We had E. But now we're dividing it. This guy inside is 3-dimensional. We chose to have dz. But then these two are 2-dimensional, which is d. That's what we're doing here. Now we can keep writing the integral. Y equals in blue. I don't have to write down y equals. Just 0. And the other one we just solved. And we got y equals, I already forgot, 4 minus 2x. 4 minus 2x. And I will write down the inequalities as well. Inequalities. Some people like to write inequalities in blue. So y is also going from small to big, just like we did before for the exam 2. Small to big. And we learned that y is changing from 0 to 4 minus 2x. The tilted part of the plane. So that was a tilted line. What do you think about that? It's interesting, we're doing lots of geometry, and I know American students are very scared of geometry for some reason. Maybe because you guys eliminated it, kind of. We just left a little bit, I think, at high school, right? We do geometry since 6th grade till like 12. So for us, it's no difference in other classes. But that's what we're doing here. So to like trying to fight the fear or try to enjoy it. That's even the best part. Finally, the last step, I think it's number 4. Yes. Let me put it nicely. This was number 3, inequalities in 2D. And now number 4 will be just numbers. Let me put it in what color? Pink. Number 4, we're going to have x. Those will be numbers. Numbers. constants. X is changing between what and what. Let me go to the same picture, so we don't need any other picture. Do you see what X is going from to? 0 and 2, that's the easiest one. Yay, from 0 to 2, no functions. From the same plot, 2D plot or picture. So we don't draw any other stuff. That's a good part of it. So I can finish my triple integral from 0 to 4. Ta-da! Look at that. Look at that. What do you think about that? There are 3 different ways how to write down this integral. So let me just a second point this out. Why did I choose this order? Why did I not choose another order?
Why is it from 0 to 2?
Oh, from 0 to 2? Yeah? Oh, that's what you're trying to say?
Yeah.
Thank you. Good catch. You see, I'm making mistakes on purpose. On my yesterday video, I solved an amazing problem. And I made totally a wrong mistake on the very start of the problem. It was x cubed and I wrote x squared. So everything was wrong, but it was right. So I just mentioned, it was right, it's fine. Just now you do as an exercise by yourself with x cubed. Yes?
Yes, I think I know why you had d, z, dy, dx.
Yeah, tell me.
Like, remember in the double integrals, when we did the double integrals, we had the equations in the integral and the numbers in the added integral. So it depends on the complexity of the equations. If the equations are more complex, you always put them in the inner integral.
Mm-hmm.
And then the number, if you have if it either x or y or just numbers, then you have them in the opposite and in the middle.
Yeah.
At least like, a 2D equation.
I like it. That's a very good explanation. So the explanation was here why we choose dz, dy, dx. I saw 6z there, so I just wanted to integrate it right away. The idea is, like before, you have some hard function. Let's integrate it right away to get rid of it. Because when you integrate through other things, it might make it more complicated. So, but as you understand, there are 6 different ways. Did I say 3 before? No. 6 different ways to do triple integrals. Remember on the exam 2, we asked you to change the order of integration. There were only 2 options. Well, I did this video from your homework. It has the name, Triple Integral in 6 Different Ways. Ton, ton, ton. This is what I show in Calculus 1 and 2 classes to let them know where all this is going. You need to know how to jump between I don't think, okay, I cannot say it's not going to be on exam because I actually don't know. But you need to be good in flipping everything. dz, dy, dx, dz, dx, dy. So you see this will stay the same. Then dx stays the same. We have dy, dz, dz, dy. And dy stays the same. Why I'm only identifying the inside ones? Because whatever is inside is 3D. That is 3D object. And after this, we're going into 2D picture. So whatever the 2 guys are standing outside, that is a 2D picture. So in this case, it's a xy axis, right? In this picture, that will be yz, and so on. So that's what makes it very creative, very interesting. And I solve this for you. Every time I'm drawing this 2D picture, y and x, and you can reuse it. Then you can do y and z. You can ask me what to put up, y or z. Actually, it's up to you. It's very creative. Cartesian coordinates, you can put them anywhere you like. You don't have to have a fixed z always pointing out. It's still going to be correct. You just need to be consistent. And the last one, z and x. See, at some point it's parabola. At some point it's a triangle. Because we're talking about the shadows. Check it out. The shadows are different with respect to different axes. Here it is parabola, but here it is a triangle. So that's pretty cool that it really matters how you are looking at 3D object, from which perspective you're looking at. And if you're looking from here, that's triangle as well. So a person who is looking at a 3D object from different side will see different things. That's a pretty cool idea here. That's what I call shadows. Officially, it's called a projection. Or mapping. Let's continue after I freaked you out a little bit. Let's finally actually solve it. So let's do that. Let's solve the integral. Let me rewrite what I got in one nice black color. We created, not professional today for some reason. Okay, now we have, I can see it in my notes. Thus, therefore, to summarize, now we have triple integral over e 6z dx dy dz was reconstructed as integral from 0 to 2, that is dx, integral from 0 to 4 minus 2x, that is dy, and finally integral from 0 to 12 minus 6x minus 3y, that is dz. There's a function inside which has nothing to do to those borders. That one was just is a input of the integration, which integrant, so we're going to be integrating that. And then we have dz, dy, dx. See, order matters a lot. dz, dy, dx. Did you notice that we can have like a very cool picture here? This piece, I already mentioned that, is 3D. Well, the other two are 2D. But you see from the upper limits of integration, has two variables, one variable, no variable. Do you see what I mean? Two variables, one variable, no variable. So that makes sense. The final answer should be a number. To have a number is the answer. The last integral should be definite integral with numbers. So it should be just 67.3 or something like that. No function at the answer. What do you think about that? How cool is that? People like not very impressed. You should try, okay? It says here, yes, see? Triple the fun, but quadruple the pain. Let's do it. Did you integrate while I was talking? So we're going to do it step by step. There's nothing new here. We do step by step, starting with the inside one. From 0 to 2 and from 0 to 4 minus 2x. I'm going to leave it alone for now. And I will be integrating 6z. 6z gives me 6z squared over 2. Bar from 0 to 12 minus 6x minus 3y. And now I only have dy and dx. Tell me, does it make sense? This is getting messy. So you see, if you're a careful, neat person who write nicely, that will help you a lot right now. Using colors also helps, called color coding. Plug the top minus the bottom. 0 to 2, integral from 0 to 4, why this 4 is so ugly, 4, minus 2x. 6 and 2 simplifies is 3. You can kick out 3 outside or keep it here. 3z squared. 12 minus 6x minus 3y. dy dx. So now what? What are we going to do now? Convert to what?
So like you have to separate the 12 and 6 plus 3 into two factors.
Oh, I see what you mean. People, what do you think? The very interesting idea. We can try to factor, to have some factoring. What else? So first of all, the question is what the heck we're doing next. We're integrating with respect to y, this whole thing, which is, here's the variable y. Everything else is a constant, so it will be just 12x, y, 12y and minus 6xy. But how do we get inside of the square? So what do you think we should do?
Just solve the square.
Solve the square, which means square of sum, right? There's a formula for that.
Wait, can you do chain rule?
Chain rule, but we're integrating. U sub, right?
Oh, okay.
That's what you meant. Because chain rule, when we differentiate undoing chain rule, we're integrating. This is chain rule, so to undo it, you do U sub. Yeah?
But there's no like thing outside of it to kind of cancel out the D, right?
Let's check. So very cool. 2 ways of doing it. So first of all, just basically step 1, admit the problem. Accept that there is a problem. Step 2, figure out how to integrate this stuff. Step 3, choose the method. Way 1, you can just actually, multiply, either use formula of squares for 3 terms. Usually people don't remember that one. Or just multiply like that, distribute, blah, blah, blah. That's too slow, to be honest. That is too time consuming, so I would not do that. I would do U substitution. U substitution says, I don't like this thing inside. It makes my life harder, so I will call it U. That's kind of why U substitution is working. Let U, can you imagine we learned U substitution in, if you took Calculus 2 class last semester and it was August. We learned U substitution in August. You said it was the hardest thing in your life, and now we do triple integrals. That's how fast this material goes, but also means that you should be very proud of your brain and of your effort in doing homework. That's how far you jump from Calculus 2 to Calculus 3. Calculus 3 is the first level of hard calculus which students take. Calculus 3 is the first level of upper level math. Whatever was below Calculus 3 comes to be lower level math. So see how fast you jumped. Just be very proud of yourself. Even if you're not doing as well as you believe, doesn't matter. This is really amazing that you can jump like that. Not everyone can do that. Remember that. du. Okay, what the heck du will be? Is it partial du or not? Du with respect to y, right? So technically speaking, partial, or you just remember that everything else is a constant. So minus 3. Okay, good. So I will write down equals. Let's not touch 0 and 2. That one is waiting. We're working with 0, 4 minus 2x. And we have 3 u squared. And then what? Times or over? Because this one is dy. Exactly. You solve for dy. So it will be over minus 3 du. Is there anything you find odd? Odd or weird? Awkward, yes. Limits of integration. Exactly, thank you. You're supposed to change limits of integration. Usually people don't do it in upper level math. Do you know? You can just finish integrating and then plug the original function. But for that to be correct, you write down the note. This is still y and this is still y. But actually it's supposed to change. You're supposed to solve for y and plug into those and change it to u. Yeah? Question? Thank you. Oh, you see, I should have asked you how to do it. So you finish integrating. That will be u cubed over 3. So 3 and 1/3 cancel out. You have 0 and 2. You have 0 and 4 minus 2x. And now you have u cubed over 3. And guess what? I'm just going to plug my u back. It's 12 minus 6x minus 3y cubed over 3 bar. So now I don't need that first integral anymore. I'm going to move. Negative? Yes, thank you. See how good I am making mistakes on purpose. It's professional already. 3y, let me kick negative outside. This is this negative over here. And I have dx bar 0 and then 4 minus 2x. In general, we just perform U substitution, but actually it's U substitution shortcut. There is U substitution shortcut, which I can remind you. I teach shortcuts in my classes if you don't know in Calculus 2. ax plus b to the n dx. It will be solved the way you know, n plus 1 over n plus 1, and then divide by the leading coefficient. That's a U sub shortcut. So that's what we did right now, but we did actually carefully. I teach it in my Calculus 2 class. You don't have to know it, but that makes it faster. So I noticed that was a polynomial. You have polynomial to the n with one variable, it's linear. You can use the shortcut. Okay, check it out, check it out. Very interesting. This never happened to you before. But you have to plug 4 minus 2x somewhere. We have 2 variables, x and y. What if you have 5 integrals? Then you'll have 4 variables, and you have to know which one to plug where. How do we know? Yeah. I would, yeah. I just decided to make it beautiful for the notes. But then I will move it. Let's move 3 outside in the next step. So I highly recommend you take a pencil and write down what the heck we're plugging in. This is y, and this is y. This small note will help your brain not to mess up. If you have 4 or 5 variables, how do you know which one we're working with right now? Well, one way to know is the one, the integrand here, the variable of integration, the previous one, tells you what we're doing. We're working with y. Or put a pencil note in the pencil. Now we know I'm plugging it here. This 4 minus 2x polynomial, I'm plugging into y, equals, almost done, minus, let's do 1/3, like a suggestions, right? Let's kick it outside. Integral from 0 to 2, let's not bother with that for now. Now I have 12 minus 6x minus 3, and in this new color I will do 4 minus 2x. Minus, be careful, the whole next part is not 0. Oh, how about cube? Now it's so messy. Let me do it here. Cube. The bar. And then I have y equals to 0 at the bottom. I still have to plug 0. So let's do that. Minus, whole parentheses, open them. 12 minus 6x. And then 3y is 0. Close. Cubed. dx. Correct or not? Check. Agree, disagree. Some up, some down, or like eh. Who's doing computer science homework over there? You can see it. Sydney, like, funny, how dare you. Anyway, let's check. The last step should have one variable because only one variable left to integrate. Do I see y? Do I see z? Do I see t, m, g? No, it's only x. We're doing fine because everything else got plugged in, so it's gone. Yes.
So what would 12 minus 6x?
Oh, see, I was wondering if I should skip the step or not. Thank you. Let me not skip the step. Minus 3 times 0 cubed. So I'm plugging 0. Top minus the bottom. Yeah, I was thinking that if I skip, it might be not obvious. Yeah, I think so too. Thank you for asking. Huh?
Actually looks nice, actually, because we can just cancel some things out.
Yeah, but yeah. Let's see. I know. Kind of looks horrible to me, but maybe it's not that bad. So we have minus 1/3, minus 1/3. Let's simplify from 0 to 2. Now I'm taking a pencil because I don't want to spend more space. Not just because I don't have a space, but it's just kind of annoying. Let's not do too much work. Take a pencil and let's write down 12 minus 6x minus 12 plus 6x. And all of this is cubed. So quickly simplifying. That means 12 and minus 12 simplifies, cancels out. 6x and minus 6x cancels out. 0 to cube is 0. So the whole first term goes away. Yay. So we end up to have 12 minus 6x cube dx. Let me wait a little bit. Only the second part left.
Wouldn't it have to be negative out in front?
That's a good point.
And then you can cancel
Do we
out
have to
negative.
have negative in front? Yes, because of this one. Good job.
And then
Right.
can't you cancel out the negative out in front so it's just 1/3?
Yeah, that's what I plan to do. It's just 1/3. Good eye. You see, people are actually paying attention. People are doing, yeah, not too bad. Can you imagine that's only one problem? We did not even finish it yet. But we're almost there. And then you repeat your substitution the way we just did before. It's the same your substitution shortcut I showed here. So, do you know anyone who, you don't have to know your substitution shortcut. I'm not requiring that. But if you do, can you tell me what we're going to have right now? 12, I will start, minus 6x to what? To the 4 over 4 times 1 over negative 6, exactly. 4 times negative 6, you're right. That's a u sub shortcut. Let me make a point that we did u sub. U sub. U sub. Bar, and we're finally plugging the numbers 0 and 2. And when you actually plug it in carefully, you get 12 to the 4 over 72, which is 288. Yay! Finally! I know, right? Finally. So Yeah. That was a triple integral over the tetrahedron, but in the first octant and cut off by the plane. Yeah.
Could you go back up to the shortcut for a second?
Yeah, for sure. You don't have to perform shortcut. You can actually do this U sub, which we did before. Like so. Okay, people. Questions, ideas, suggestions. That's the easiest chapter from the chapter of triple integrals. Because we're gonna do polar on Tuesday, so that will mess it up even more. Polar is coming too. dr, d phi, d theta is coming. And that is very popular engineering, so we always cover that. Yes? The idea? Oh. Oh, I just chose it to be. So you can choose any. Just like before, we told you. Okay, people, let's try to concentrate. It's a very good question about the order. How do we know which order to do? You choose one. So this is a homework example. And no, it is the one. And you can do it in any order you want. So you kind of choose which one you prefer. And I prefer, since I saw there's a function in terms of z, I decided to get rid of it right away. So I decided to choose dz to go first. And from there, everything follows. But that's not necessary. I could do dx to be first. The whole point is the moment you choose whatever goes first, for example, dx, this is a 3D object now. So x will be for this 3D tetrahedron thing. On the floor, x is changing from a function to a function. And then this will be 2D. So that's the only part. You need to make sure which one is easier. And usually dx dy into d is easier because we got used to it for like 5 years of doing dx dy Cartesian coordinates. So that's why it's nice to have this one to be in 2D because our brain is good at that. But that's actually not a good thing. It's a drawback that we got used to one thing. It's hard to work in 3D. Our imagination has to have time to adjust. So imagine drawing z and y. It is possible and okay. I did it in this example. But it takes time to adjust to it. So you're like, I would rather do dx dy. But to do dx dy, z have to disappear first. Very good question. Thank you. Yes?
So it's always like one problem for pages.
One problem for what? Oh, 4 pages. Sometimes it's 5, so not always. So no, the answer is no, don't worry. Sometimes it's more than that. This was, we're gonna go to polar. That will be interesting as well. Yes?
So for all those different integrals, all the different ways it can look, for the problem we did, it seemed like our 3D limit of integration, so the dz for us, that looks like a 3D thing.
Oh, not this. I know what you're asking. Well, you did not finish. Sorry, I already know what you're asking.
But when you go over to all the different
I can show you.
It doesn't look.
No, it's possible. Okay, people, you're too happy. Okay, concentrate. That's a weird class to be happy. We don't do any volume of the ice cream yet. So the question is, if I do dx first, where the 3D thing is coming for? Check it out. The 3D will be that wall over here towards me. The wall is a 3D object in space. And this thing is also 3D. So it will be back to front. That's what we have to calculate, those 3D functions. If I do dy first, then from the right towards here will be the 3D thing. So z was the most natural to see because it's height. But technically speaking, height is whatever you're going to flip it and put it height. You can have depth and frontness, whatever that thing can be called. So depth in different directions.
So you just solve for x.
Yeah, and you keep the whole process again. Exactly, you solve for x and blah, 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 blah. And then go to the 2D and repeat everything. So that's why. Good questions, people? Okay, let's move on to more stuff. We're gonna go to some physics applications. That's actually why we're teaching all of this. Not just to torture you, but actually there's applications there. In general, triple integral does not calculate a volume. That's too complicated. Volumes are done in double integrals. It calculates a hypervolume, which is 4-dimensional volume, under the function. In this case, it was 6z, which was in the 4th dimension, and over 3D dimensional object, which was tetrahedron in the first octant. Think of the base as E and the height Z. So this is the most interesting thing to explain. So try to concentrate. Check it out. That is kind of mind-blowing, a little bit literally, so hold your brain. This is what happened. We had this tetrahedron, right? Here it is. In the first octant, we just worked with that thing. That is a domain for some 4-dimensional object. So whatever we used to have in calculus 1, find the area below the graph. We used one integral, right, from A to B, and we found the area. That was this thing. The domain was 2-dimensional from A to B. Then we decided to add one more dimensional with double integrals. Find the volume, we said. It was like a 3-dimensional bulb, and then whatever the shadow was below, we integrated over the shadow we called A. It's still domain, but domain was 2-dimensional. What if domain is a 3-dimensional object? So what then the volume does even mean? That will be a 4-dimensional volume. So this is how I see it, and you can see it your own way, and maybe explain to me later, and I'll share it with everyone. Usually what I see is a shadow. This is the roof, for example, roof of the parking lot. And then I want to know how big the shadow it makes, so I know how many cars will be covered by the shade, right? Shade. So this shade is a domain. It will be one integral from A to B. In 3-dimensional way, it will be the same thing. This is a roof, right? Now it's just more smart. It's not just line. It's actually a 3-dimensional object, a roof. And it makes a shade for cars. And now it will be double integral from A to B, C to D, or functions, right? What if a shadow is a 3-dimensional object, which is left by a 4-dimensional object? So a 4-dimensional object from some kind of view. Remember that the shadow only shows up from some kind of view. If sun is over here, the shadow will be like that, right? So only when I'm looking from the top, I see the shadow from A to B. Only when I'm looking from the top, I see the shadow as a square or whatever that thing is. So when I'm looking from some kind of top, what is even top in 4 dimensions? I don't know. From some kind of way, I'm looking at it, and the shadow that the 4-dimensional creature leaves in front of me is a 3-dimensional tetrahedron. That's a cool idea. So you are a 3-dimensional object walking around. What if you are a shadow or projection basically from a 4-dimensional creature? Isn't it cool? So the idea is on the board, if you think about it. So I have whiteboard, right? The 2-dimensional creature is walking only left and right on the board, up and down. The moment I'm taking this object away towards myself, for the 2-dimensional creature, it just disappears, right? It disappears, and then I'm putting it back on a different location. So it just teleports to another place, and a 2-dimensional object is shocked about that. Like, it disappeared, so someone who is looking at that, disappeared and showed up. So for the 4-dimension, it'll be the same thing. In 3 dimensions, you are walking around, and then you disappeared, and then you show up over there. That means you went to the 4th dimension. That's what we're doing here right now. We're just increasing 1 dimension, not even 5, not even 6, and it's already confusing. That's how primitive human being brain is. It's hard for us to understand, visualize, or sketch the graph, or code upper dimensions. But mathematicians are so brave. We work with n dimensions. We work with infinitely many dimensions. So I was proving a theorem in Ukrainian University for n-dimensional matrices. Matrix not 3 by 3, 5 by 5, but for n to n. And the next step of my dissertation was supposed to go to infinity, infinitely many dimensions, matrices from infinity to infinity. But then I went to America and ditched that project. So I went to genetics instead, mathematical genetics. So my idea is, what is the volume between four-dimensional object and the shadow it makes, which is three-dimensional object. That is the idea. What is this hypervolume? You know, that is the idea. Well, you don't have to be scared because, well, what I wanted to say is this four-dimensional object is 6. So the volume is done below 6z, which is four-dimensional object, and above this tetrahedron. So below and above gives you a volume. But what kind of volume? It's hypervolume. That is the idea. It has lots of applications, which I will tell you in a second. Literally, we don't have to imagine hard stuff like volumes, hypervolumes, and stuff like that. We can just add a dimension like a temperature. I keep mentioning this example of your body, right? Your lungs are three-dimensional objects, but the temperature of your lungs is higher than the temperature of your brain, for example. So that's a four-dimensional quality. So that is also can be calculated using three integrals. Moreover, the temperature of your liver is, and the density of it is not the same everywhere. It's not homogeneous. So it's a little bit thinner in some part of the liver and a bit thicker in another part. And that's why when people perform surgeries and they put a person to coma for some specific rare cases, the liver gets hurt a lot. And sometimes the patient dies after waking up from a liver failure because some part of it just did not have enough oxygen or temperature and died, while other part was fine. That's actually one of the optimization problems in medicine. So that's very applied, and that's why triple integrals are everywhere in architecture. I met several people who retired from architecture or working in architecture. They do triple integrals every day. So if you're a civil engineer, good luck. You'll be doing it all the time. So some idea is here. If you don't have to write it down. I give you those notes anyways. They're all in modules. Triple integral, and there's an R below everything. R is a region in 3D space. 3D space. F inside of the function is a scalar value function which takes points in three-dimensional space as the input. F swallows, that's how I usually teach in calculus 1 or pre-calculus. Input is what it's swallowing and spitting out the output, right? Something in 3D. So 3D now is the input. dV, this guy over here, is a tiny unit of volume. In Cartesian, this is expanded to dx, dy, dz, one of the units. As with double integrals, the bounds of inner integral will be functions, and the outer integral, the outside one, are variables, numbers. These bound functions are what encodes the shape of the whole thing. Whew, finally, write down this theorem fact. That's a physics fact. You will be asked to find some mass and density and whatever, because as I told you, higher dimension doesn't have to be geometrical object, geometrical quality like hypervolume. It can be mass, it can be density, viscosity. Do you know what viscosity is? So honey has different viscosity than water, right? When you drop it, honey is actually making spirals. So spiral behavior is also coded, calculated through double and triple integrals, viscosity. If E, put it below like this. If E is a solid with density F, so F inside is a density, then mass of E can be calculated using triple integral. So something has density that's inside of the integral. And then the mass will be calculated using triple integrals. So we're going to do that. Example. Between. Find the mass of the solid E with density 2z between two paraboloids. Paraboloids is whatever is made with parabola. When it's spinning, becomes like a cup. That's called paraboloid. Yes?
So if you integrate like mass once, you get area, and then you get volume and then density.
Interesting idea. I think you're right. Depends on what's inside though. So in this case, so heaviness of the object depends on the density, right? So that's why it should be, whatever is inside now matters. Yeah, very good point. If you integrate once, it's area, twice it's volume, 3 times it's how heavy the object is. Yes, if you're integrating density. And there are other things with viscosity, with liquids, and heat equations also have their own stuff there. So yeah, finally, in upper dimensions, remember I told you this example of the hypersphere. So every time you cut something, you decrease the dimension. When you have a 3D dimension, I would say, the watermelon example. I always mention the watermelon example. The watermelon is a 3-dimensional object. You cut a slice now is 2-dimensional. It's flat. You can put it on the floor. So the 4-dimensional hypersphere is when the sphere is a 4-dimensional object and it falls of spheres, which means every time you slice a 4-dimensional watermelon, each slice is a 3-dimensional watermelon. So every time you slice it, it becomes a smaller watermelon, but now in 3 dimensions. That's actually one of the best visualization I got into, and I really liked it. Let me show you that again, in case you don't remember, but hypersphere is one of the funniest things to show to students. It looks pretty awesome. Type GIF. This is my favorite one. So this, I did not load yet. It's slowing down. This is a hypersphere. It's full of spheres. So every slice is a watermelon. 4-dimensional watermelon is a 4-dimensional object. If we want to see 4-dimensional object, we only can see it with plotting or mapping 4-dimensional object into any of our 3D parts. So we only can check the shadow of it from this side, this side, this side into 3D. So in this case, it's slowing down, that's why. It's not moving. So sad. In this case, it's 4-dimensional watermelon, and each slice is a watermelon. How cool is that? Anyway, let's start this problem and finish later. This is the picture. 2 paraboloids. We used to have 2 parabolas, and we ask you to find area between those in calculus 2 class. In calculus 1 and 2. So we have this, but now we increase in dimension. Now there are 2 3-dimensional objects. Paraboloid looking up, paraboloid looking down. How do I know that? Because one has negative signs and one has positive signs. Basically concave up and concave down idea. So they intersect and create this nice looking blue blue object in 3D. So steps. What are we looking for again? We're looking for the mass of the solid E with given density. Density is also a function, because guess what? The density of your stomach is not the same everywhere. Density of your bones. Do you know your bones don't have the same density? Some bones break easily, while others are not. So that's different density of the porous part of your bones. Means it's not a constant. It's not like density of your bones is 3. No, it depends on the location. So in this case, it's a function 2z. And we want to find how heavy is this object, E. This is the object E with a given density, which is not a constant. Step 1, sketch. You don't have to be precise. 3D. Well, I just did it for you. Here's copy-paste, amazing sketch. 3D. And immediately figure out where is your Z. Again, you can do triple integral in any order. dz, dy, dx, but it's easier to do dz first because it's usually more natural for us to do dx, dy into d. And for other reasons too. Let's see, where is my z running from? Well, like duh, they're given. And that's why I feel it's natural to get rid of dz first. Z is running from the... Which one actually? You tell me. From which z to which z?
10 minus.
Careful. From 10 or x squared. So the one below is the red one. Yeah? So that's a pretty cool trick here. Not the one that's below written, but the one that's below started. So remember, from small to big or large. Good job. X squared plus y squared plus 2 goes first because it's a cup looking up. And a cup looking down is the roof of this three-dimensional object. 10 minus x squared minus y squared. So we're already done with this part. That means I can write down the integral. And the middle integral is already from x squared plus y squared plus 2, from small to large. 10 minus x squared minus y squared. You can say it from the bottom to the top, but in general, it's from small to large. Left to right, front, back, it's small to large. 2z, keep it, that is given. We don't care about that for now. And we finished for now dz. So three-dimensional part is done. Now we can do dx dy or dy dx. That will go into 2D. Does it make sense? People are like, I just want to go. It kind of makes sense, but I want to go. Step 2. 2D. After this, you can go to 2D. You need to draw a picture in whatever variables left. I'll put it in purple color. Dx dy. Whatever is left, that's what you're drawing. Dx dy. See? Whatever. So, two-dimensional object will not see this three-dimensional object. Two-dimensional object doesn't see 3D. Two-dimensional creature sees the shadow of the three-dimensional object somewhere. Some kind of projection. Either we're projecting that way, then it will be one thing. That way, it will be another thing. It's like seeing an elephant from different sides. From one side, a person sees a nose, and like, whoa, what is that? A nose with a huge ears. From another side, it's a butt. Like, what kind of creature is that? So that depends, that is important. And from front and the back of the elephant, you feel like elephant has only 2 legs. That's also important. That's the misleading idea if you don't have enough information. Elephant has 2 legs from front and back. That's why it's so hard, and that's why it's important to see all dimensions. So we are projecting it down to x and y axis, right? To the floor. What does a two-dimensional creature sees when it looks from the top down? A circle. Is it just the outside part, or it's a filled in, or with the edge, without the edge? What do you think? Seems like it's a disk. So if you have a sun over here, right? The shadow, which called the projection, will be this nice circle. How do I know? It will be this big. As big as the biggest intersection. And it's not hollow, which means it's not empty. It's solid. So that's what we call the disk. The disk looks like this and like so. That's called a disk. It's filled in. You can write down the equation of that disk. Well, it's centered at 0, 0. If you put it in a 0, we just need to know the radius. So it's definitely x squared plus y squared equals something squared. How do we find out that? Yeah, exactly. These are the same, right? So we can set them equal to each other. Z is 0 anyways. There's no z here, it's 0. So we have 2 plus x squared plus y squared equals 10 minus x squared minus y squared. If you simplify that, it becomes 2x squared plus y squared equals 8. Divide by 2 equals 2. 4. Because, and you see, we found intersection of 2 paraboloids, and that gave us the biggest radius possible. Yeah. So, I will finish, actually. It's not that... there are 2 ways of doing it. Way 1, we actually stick to whatever we're doing right now, and we do that x, if we do dx first or dy first, doesn't matter to me, and that it should not be matter for you either, because you learned both, dx first or dy first. If dx goes first, x is changing from a function to a function, from minus square root to plus square root, right? And then y is changing from minus 4 to 4. Same with y. It's from minus squared to y squared, and x is from minus 4 to 4. So let me write it down, and you can check it at home. However, so let me do 2z, dz, dx, dy. We already agreed on x squared plus y squared plus 2 and 10 minus x squared minus y squared. That was z part. X is from minus square root to plus square root because it's half of the circle, right? And then y is height from minus 2 or 4? 2. And I said 4, remember, so that's also was wrong. From minus 2 to 2. So that's how you would do it if you didn't learn polar equations. This is a double integral. So actually for double integral, we do know formula for polar equations, which is r d theta. And we can actually just rewrite using polar equations. That was on your test last time. In polar, it's easier to calculate. It's going to be r d theta, skip some space, and then the double integral we're basically going to double integral is r is from 0 to 2 because it's radius, and theta completes the whole cycle, so it's from 0 to 2 pi. The only problem is the inside integral. We have to figure out what to do there, and I don't think you want to do it right now, so let's do it later. So we're gonna keep that. You can finish it at home and then bring it into class next time. So either you finish it using stupid square roots, which might not be possible, but that's why every time you see a circle, paraboloid, sphere, you do polar for that reason, not to have to bother with square roots. Good job, people, for surviving 2 problems. Anyone come here? Thank you. Yeah, we did not finish. I was talking too much about lungs and watermelons.